Welcome to the training of maximum power point trackers and common topologies. This training will start from the structure of a silicon photovoltaic cell and focus on MPPTs, common topologies, and using MPPTs on solar cars. Contents of this webinar will be about the structure of a silicon photovoltaic cell, mathematical models of a PV cell, variable electrical power source and load, topologies of MPPTs and MPPTs on solar cars. Most common photovoltaic cells are polycrystal or monocrystal silicon cells. Silicon element has the atomic number of 14 and has 4 bonding electrons. In a single bond, the silicon atom contributes just 1 electron to the bond. It can therefore form single bonds with 4 neighboring atoms. Polycrystal silicon cell is formed with many crystals, whereas the monosilicon PV cell is formed using one seed silicon. After forming the silicon crystal structure, which is very poor, N-type and P-type layers are formed by doping processes. As an example, phosphorus can be used for forming N-type layer and boron atom can be used for P-type layer. It can be easily noticed if a PV cell is produced using polycrystal or monocrystal structure by looking to the surface of the PV cell. A solar cell or a photovoltaic cell is an electrical component that converts the energy of light directly into electricity by the photovoltaic effect. The photovoltaic cell is generally a constant current source which is directly proportional to the solar radiation falling on the cell. Equivalent electrical circuit of a solar cell consists of 3 layers. These are N-type layer, P-type layer, and depletion layer. Depletion layer is the middle layer and the one connects the both pole layers using the photon energy. N-type layer is the layer which has free electrons and P-type layer is the one which has holes for electrons. Photon energy converts the semiconductor structure into a conductor and also converts the light into electricity at the same time. Equivalent circuit of a PV cell can be simply modeled as a current source in parallel with a resistor and a diode. Those are connected in series with another resistor. The output of the current source is directly proportional with the solar radiation falling on the cell. The open circuit voltage of the cell is quite different from the cell that is connected with the load which is shaped with RS resistor. Besides, the temperature affects the output of the cell as well. On the other hand, the mathematical model of the cell is defined with the Shockley diode equation in most of the research about PVs. To understand the one-diode model, we can go into details. Firstly, we know that the cell is a constant current source formed with a semiconductor structure and the generated current increases with light. We can define the current generated by light as IPH and the current can be used as I. Since the structure is a semiconductor structure, there should be a saturation current like in the diode equation. The reverse saturation current is IO in the model and it is defined with the electron charge Q, diode voltage V, Boltzmann constant K, cell temperature Tc, and diode ideality factor A. In fact, the blue part of the PV cell model is Shockley diode equation which defines the characteristics of an ideal diode. If we add the current generated by light to Shockley diode equation, we have the simplest PV cell model that is indicated with green rectangle. But this model is not so accurate and it is ideal, because for this model there is no opposite current passing through the PV cell structure or decrease in current, and also there is no voltage drop. For these reasons, a shunt resistor and a serial connected resistor are added to the model to make the model more accurate. The model with the red rectangle is the most common PV cell model. Photovoltaics are electrical current sources and solar irradiation determines the energy which the PV generates. If we look at the first graph, we can see that the current is directly proportional to solar radiation received by the surface of the cell. And in the second graph, it can be seen that the increase in temperature decreases the open circuit voltage of the cell, so the energy it can generate.
Cells are connected to 4 modules. Serial connection of cells increases the open circuit voltage. It must be kept in mind that if the level of the output voltage of the modules is just above the nominal voltage level of the load or has the same value of the maximum voltage which can be received by the load, the total efficiency of the system will be higher in most cases. If there is a need of more current by the load, cells can be connected in parallel. In this case, short circuit current increases proportional to the number of the parallel connected cells. PV cells form PV modules and PV modules form solar arrays. Types of module connections are decided considering the input voltage level and the current level of the unit which will be connected to the solar arrays.
Diodes are used in PV module connections. Cells generate current directly proportional to light reaching the surface of the cell. If some parts of the array are under shade, all modules connected in series have to have the same current as the least generating module. But if bypass diodes are used in all serial connections like as in figure, the module under shade can be bypassed so that the rest generates energy. Blocking diodes, on the other hand, is for protection. If an array is connected directly to load, which can also source like a battery pack, and the array doesn't generate energy at the moment, blocking diodes prevent the current flow in opposite direction and the damage of modules. Current of the PV cell varies with the solar radiation falling on the cell. Since the power is the product of current and voltage, change in current causes change in power output. A constant DC-DC converter has a disadvantage in varying solar irradiation levels since the maximum power point changes. In this graph, dashed white line shows the current output of the PV module, whereas the continuous white line is the power generated due to the increasing voltage of the PV module. Depending on the instantaneous power needs, load lines differ. In this graph, load lines of two different states can be seen. The intersection point of load line and the current source curve is called as the operating point. In both cases, the operating points are not at maximum power points. This means that the PV module is not used efficient enough and there is a controller need to correct this. The device which tracks the maximum power point is called as Maximum Power Point Tracker or MPPT. There are different algorithms and topologies to provide this. There are four common DC-DC conversion topologies in MPPTs. These are buck type, boost type, buck boost type, and chuck type.
A DC-DC converter is an electronic circuit which increases or decreases voltage or current due to the load side needs. A buck-type DC-DC converter is a voltage step-down converter. Since the power is the product of voltage and current, the current is stepped up in buck converters. When the switch in the circuit is on state, the current increases, so the inductor produces an opposing voltage in response to the current change. This reduces the voltage across the load. When the state of the switch is off, the voltage source is disconnected from the circuit and the current decreases. The change in current produces a change in voltage through the inductor. During this time interval, the inductor discharges its energy to the circuit. In buck-type MPPTs, solar array has higher voltage level than battery side. A boost-type DC-DC converter is a voltage step-up converter, which means also that the output current is lower than the input current. When the switch in the circuit is on state, current flows through the inductor and the inductor stores some energy by generating a magnetic field. When the switch is off state, the increase in impedance reduces the current. To maintain the current through the load, the magnetic field is used. The polarity will be reversed, which results as two sources will be in series. This causes a higher voltage to change the capacitor through the diode. In boost type MPPTs, better side or the output voltage is higher than the solar array side. A buck boost type MPPT is equivalent to a flyback converter using a single inductor, and a topology is a combination of buck and boost types. When the switch in the figure is on, all the current flows through the switch and the inductor and returns back to the source. When the switch in the figure is off, the polarity of the inductor is reversed. The energy stored in the inductor is released and dissipated on the load resistance. In buck-boost type MPPTs, the output voltage can be greater or less than input voltage. It has advantages like capable of covering entire IV characteristics, but the efficiencies are not higher than buck or boost types. When the power increases, the efficiency of the buck-boost type decreases dramatically. For high-power applications, Chugh converters are more efficient. Chugh converter is a negative output capacitive energy flyback DC-DC converter. It is developed from the basic buck-boost converter. The difference is that it uses a capacitor, not an inductor, for storing energy and transferring power. Main disadvantages of the Chugh converter are inverting the polarity of the output, besides the high current flow through the power switch and the diode.
The most common MPPT algorithm is the hill climbing or perturb and observe algorithm. In this method, it is aimed to reach the top of the curve with changing the voltage volume. Perturbation is applied to array voltage. Algorithm starts with measuring voltage and current of the solar array. Using these values, the power is calculated. Then a new voltage output value is chosen. Current is sensed for the new voltage value and new power value is calculated once more. In observation step, it is compared if the new power value is greater than the previous one. If the new power value is greater than the previous one, baseline voltage value is replaced with the new one. But if the new voltage value results with lower power, then the delta value is subtracted from the initial voltage value and new power value is calculated. The new power value is compared with the previous one and the whole process continues again and again. This method, however, has a disadvantage of cannot tracking in fast changing solar irradiation, and there are hybrid techniques to prevent this disadvantage.
Since the chosen voltage value can be on both sides of the maximum power point, the conditions must be written carefully. In order not to stuck on the local maxima during irradiation changes, delta value can be adaptive. Solar cars are the vehicles which generate the energy need of traveling from the sun using photovoltaics. Since the surface area of the photovoltaics of these cars are limited to 4 square meters of silicon solar arrays in regulations of most of the solar car challenges, the total power of the photovoltaics on these cars are generally around 900 watt-peak. Generated energy is sent to a battery pack and motor driver using MPPTs. During travel of the vehicle, the source and the load sides are varying instantaneously. As for acceleration, they have also a battery pack which is limited to 5 kWh. The instantaneous energy need of the vehicle and the changing solar irradiation determines if the energy generation should be used to travel or to charge the battery. These cars are highly efficient vehicles which can reach up to 150 km per hour with having nothing more than a 2.5 kW hub motor. In these cars, MPPTs are highly crucial parts. The semi-flex silicon panels on solar cars are divided into 2 or 3 regions. Each group is connected to a separate MPPT. Buck type and buck boost type of MPPT topologies are also used, but boost type MPPTs are very common in these vehicles because of its advantage of efficiency, simplicity, and easy to detect fault. There are also interesting research like using boost-type micro-MPPTs on solar cars. In this electrical schema, there are three parallel MPPT groups. Each MPPT group has 5 serially connected MPPTs, and each MPPT is connected to 2 serially connected PV modules. The idea is to decrease the loss for partial shading and preventing the loss of whole 1 PV region. MPPTs on solar cars are designed considering the fast-changing energy needs and weather conditions through whole challenge. Their efficiencies are higher than 99%.
Thank you for your attention and have sunny days.